Yes, yes, ma'am. We are live on YouTube now.
Okay, Professor Hashmi, could you please switch on your video for a minute?
Okay. Yeah.
Yes, sir. Yes, sir. It is on. Thank you so much. So, welcome everybody to this evening of Learning Physics with Conceptual and Problem-Based Approach, organized by the National Academy of Sciences India, NASI Delhi chapter. An 11-week course which started on 27th of July 2020, and presently we are having the week of atomic physics and thermal physics. And there are new attendees also within our audience. We are also being watched live on the YouTube at Nasi Delhi chapter every day at 5 p.m. So it's a pleasure for me to introduce Professor Hashmi to the audience. May I have the next slide, please?
Yes, ma'am.
Yes. So Professor Hashmi has been working in the Department of Physics and Astrophysics, University of Delhi. After obtaining his PhD degree in 1988 from Banaras in the University Varanasi, his research work involves fabrication of magnesium and sodium rechargeable batteries using gel polymer electrolytes, development of solid state and flexible supercapacitors based on carbonaceous materials, and conducting polymer electrodes, development of thermally and electrochemically stable polymer electrolytes, and their application in energy storage devices. He is one of the members of expert committee for project evaluation of young scientists and Inspire Fellowship evaluation for physical sciences subject at SERB, Department of Science and Technology, New Delhi. He has published several research papers in various international journals and has authored 2 books on the topic of materials and devices. He has also collaboration with prestigious national and international institutes. Welcome, sir. It's a pleasure to have you here. Professor Hashmi is well known for his course of atomic and molecular physics, which he generally delivers to the MSc students of Delhi University. And hence, I've requested him to kindly shower knowledge upon us also, and also enlighten us in how we should go about it. So it's a wonderful opportunity for revision of MSc level atomic physics and BSc level atomic physics, and gives us an insight on how to go about the subject. Welcome, sir. Dr. Divya,
Very
please
warm
stop sharing.
welcome, sir. Yes, ma'am. Yes,
Please
ma'am.
stop sharing the screen.
Yes,
Sir,
ma'am.
now you can start sharing your screen.
Okay. Okay. So, thank you very much for your nice words about me. And now I am in a process of sharing my uh, lecture today, what I have to deliver. So, I think that I've done it well. So, this is the. So, should I start, Dr. Sunita?
Yes, sir, please.
Yeah. So, welcome you all in this class once again to this atomic and atomic physics. And in continuity of the previous class, that I have tried my level best to make you points clear. Maybe that I am successful in that regard. That I have started from the very basic introductory remarks of the atomic physics, that from where these inventions started and how the theoretical model and experimental research were going on in parallel. And that was the beauty of this field, that wheresoever experimental work was required according to the theoretical prediction, the people have done it, and wherever the theoretical modeling was required for the explanation of the experimental research, it has also been done. You know that uh, after the some basic glimpse of this atomic physics, I had come to a topic that Schrodinger equation and the and overall, that is quantum mechanics is useful to solve many problems, atomic physics related problems, and what was not possible with the classical mechanics. And the so after the Bohr's model, several developments were taken. The one of the development was that you know that the whenever you record any emission spectra or the absorption spectra, and then you use a very powerful resolving power, having a good resolving power spectrometers, then you are able to see very fine structure in the line spectra, even certain kinds of splittings, certain level shifting, and so we are discussing this time that how the this thing can be discussed theoretically. You have seen that after the invention of very powerful spectrometers, certain lines were splitted and shifting, and then it has been started thinking of that the non-relativistic approach is not sufficient to solve the Schrodinger equation. Rather, the framing uh, the Hamiltonian in non-relativistic thing is not sufficient, and so certain corrections are were required, and these corrections one by one we are looking into it. So one of the corrections we had seen, and we discussed thoroughly yesterday, that the kinetic energy part. You see, once we had introduced the relativistic effect on kinetic energy part, which is also called the correction, then through this slide we have discussed that even first order of uh, the correction in the Hamiltonian is enough to describe many important things. And so we have found that the first order correction, that H1 dash had been taken as the correction term in the Hamiltonian. And then after that, we had solved that uh, this thing, that how much energy shift has become uh, because of it is theoretically predicted because of this first correction. And we had found the expression that this delta E1, that is the energy shift due to this first order correction, can be expressed in terms of in this expression in the atomic unit. And atomic unit, are you right in Rydberg? There is a minor difference in that both you examine and you will find that this energy term, this energy shift, depends on the principal quantum number. Where one thing is very should be very clear, that non-relativistic Bohr model had given only the energy in terms of principal quantum number, that is in atomic unit, minus z square by twice n square, or in Rydberg minus z square by n square. But if we introduce this first order correction in kinetic energy, which is also called mass correction, then we find this shift in terms of delta E1, and this depends upon not only principal quantum number, it also depends upon the orbital quantum number small n, and rest is the discussion. So this was the discussion yesterday, and then we proceed that okay, in order to frame the um, Hamiltonian, one more physical aspect should have um, to be considered, and that at that time people left it, and that was very important, and that is the spin orbit interaction. In that spin orbit interaction, we discussed in length, and we have found that the another correction term should be considered, which is written in this form, that is H2 dash is equal to half ZE square by M0 square C square R cube, and the main important factor is L dot S, these two angular momentum. So the two angular momentum is spin and the orbital angular momentum is important of this important part of this second correction, H2 dash, because of this spin orbital interaction. So that has also to be added to the Hamiltonian, and it will lead to another energy shift or the splittings if we do it the mm, take the expectation value of that for converting it into the energy value, and then from this detailed analysis we did it. I'm just recapitulating it so that you be in continuity from the previous lecture. And then we had seen that from this background of the quantum mechanics, we had been found this delta E2, that is energy shift because of this spin orbit interaction, can be written in the form of uh, the L and N, that is the principal quantum number, orbital quantum number, and J, which is a quantum number associated with the total angular momentum. Okay, so here, if we add this delta E2 to the shifting or H2 into the Hamiltonian, the value of the shift or the correction in energy is not only depending upon principal quantum number, it is depending upon the spin quantum number also, orbital quantum number also. Spin is directly not seen here, but it is inhibited inside the value of J. J is L plus S. And so you can see from this expression that we have simply simplified in terms of this non-relativistic energy En, and multiplied by factor. And then we discussed yesterday that this delta E2, the energy shift, is not valid for spherically symmetric the S shell. That is it is not valid for small l is equal to. And we explained last time that once small l is equal to 0, means that angular momentum capital L is also 0. And so the H2 term, the H2 dash term, that is the correction in Hamiltonian due to spin orbit interaction, will also vanish. So it is only valid for the higher orbitals like P, D, F, and others, not for the S orbital. So now something more to be discussed, what it has not been discussed yet. Then from this expression, you can see it can further be simplified according to different conditions. That you see that J value has two possibilities in this case of one electron system, hydrogenic system. J, you know that it is either equal to L plus S or it is equal to L minus S. Here, the S is half, so either S is half here in this case is a single electron system, one electron system. So, you know that if we are going for the two electron system, many electron system, this this spin angular momentum will no more be only half, rather it will be a combination of the halves. And so you see that J will be L plus half and L minus half. Two possibilities are there. So in that case, when J is equal to L plus half, then this factor you examine, this factor only, the numerator of this J into J plus 1 minus L into L plus 1 minus 3 by 4. Then it can be reduced to small l. You can see that for J is equal to L plus half, if you put the value of J here and rest is the same, just expand it, the whole uh, term is reduced to small, only one l. You can do yourself and see that. Well, if L is equal to L minus half, the same thing can be repeated for J value and then L into L plus 1 remaining same. And then once we shall expand, then you will find that this whole expression is reduced to minus in L plus 1. And this factor here, will have two possible values in terms of L only, that when J is equal to L plus half, that is a factor. So remaining, the factor will remain same, and it will be multiplied by L if J is equal to L plus half, and minus L plus 1 when J is equal to L minus half. Okay, and so delta E2 can be expressed in terms of atomic unit. Then we can accordingly change it here. Here, En is expressed in the atomic unit or in Rydberg. Accordingly, this expression will change. Well, as I told you earlier that when L is equal to 0, then delta E2 will be equal to 0, because this expression will be equal to 0, because capital L is 0 when L is 0. This is already explained. So this was the thing what we discussed about the uh, spin orbital. So kinetic energy interaction, spin orbit interaction. Uh, well, so if I'm not properly audible, you please check me sometime in between. If it is okay, then is it okay, Dr. Punita ji? It is okay. Hello.
Yes, sir.
Hello.
Yes, sir.
Yeah, it is. I am audible properly, na?
Yes, sir. Yes, sir. You are audible.
Yeah. It's okay. Okay. Yes. Yeah.
Sir,
So,
it's a request. Kindly, if you can turn on your video.
my video.
Yes, sir.
Just a minute.
Yes, sir. Yes, sir. It's
Is it
visible.
okay? Okay.
Yes, sir.
Okay. That's okay. That's okay.
Sir, it's because we are also live on YouTube, no? So it
Okay. Okay.
to students it may they may,
Okay.
yes.
Okay. So how to go back? Um,
Sir, your screen is
Right.
visible. You can click on the screen where you have shared.
yeah. Okay. Okay. Okay.
Yes, sir.
I found probably. What is that? How to go back, ma'am?
Sir, back to what?
Back to means to my back
Sir?
to my slide. Yeah.
Sir, a slide is visible. What is visible
It is
to
visible, but it is not visible to me.
you? Okay, sir. Then you must be seeing somewhere a button called stop sharing.
Yeah. Yeah.
In red color.
Yeah. So you
Yes.
stop sharing and then start sharing again.
Okay. Okay. Hmm.
Sir, could you manage?
Okay. Okay. Yeah. Yeah.
Yes,
Now
sir.
is it okay?
Yes, sir.
Yes,
Yeah,
sir. It was visible to us. Probably it.
But when I had gone back, then it was I was not coming back again to the
No
slide.
problem, sir. These are technical things. Please go ahead.
Yeah. Okay. Okay. Well, so after that, relativistic correction. What I have to tell you today, uh, that is the correction into the potential energy. You know that in the beginning I told you that in the Schrodinger equation or in the Hamiltonian, this is the kinetic energy part. Now we shall talk about this potential energy part. It also needs correction. So what kind of correction is required, I will discuss in detail. So actually the spin orbit interaction was additional requirement. Now I am coming to the relativistic correction due to potential energy. So uh, this relativistic correction is related to the fact that it is useful for L is not equal to L is equal to 0. So as spin orbit interaction was not for L is not equal to 0, now this correction is for L is equal to 0. So when L is equal to 0, then magnetic moment will also, this magnetic quantum number will also be 0. So we shall concentrate only the wave function for hydrogenic system to this psi 100 and this one. But this term exists for L is equal to 0 because this radial part is a non-zero value at R is equal to 0. So that's why it exists. And you see that if we consider only R is equal to 0, then it exists like this. So secondly, that you know that this spherically symmetric s orbital, doesn't lie only to ground state. It lies to higher state also. That at every state this s orbital, whether it is Earth orbital exist or not, means that is P, D, and F. Like we can have a generalized notation psi n 00, and so if psi 1000 is this one, then psi n00 will be this one n cube will be introduced there. But in this correction, one important thing is to be noted that potential energy term, if we consider the term, it is equal to uh, mm, ZE square by 4 pi epsilon 0 R. All other parameters are very well known and constant, but R is variable. So potential in that, if suppose we are choosing electron as a pointed charge, so the question is this, that whether electron is really a pointed charge, means that its location should be fixed with respect to the origin in any frame of reference. And so, is it possible for us to locate the position of the electron at a very fixed position, that is the can be really regarded as a pointed charge? Means suppose like in this figure, if we assume that the electron is lying at this point, and with respect to the origin its distance is r, really is it possible for us even experimentally in the experimental way, that really it is lying at this point, or we are helpless to consider the electron as a pointed charge? It will lie anywhere, somewhere, in a spherical ball somewhere. So it has been considered that no, it is not possible to locate the electron. It is an indistinguishable particle. You cannot distinguish it into any system very clearly and fix the position of the electron. So, what is the most probable location of the electron? What is the most probable region of the electron where the electron can lie? So, what is the minimum region where we can authentically say that electron will lie precisely? So, that has been found uh, by the scientists, that this region is actually, it is a spherical ball of the radius equal to Compton wavelength. Means that if you assume the Compton wavelength of the electron as a radius and then make a sphere, the most probable region in which electron can be located is in this ball. And this ball is known as fuzzy ball. So this is region where electron will be maximum probable location it has. So it means that there is a uncertainty into the location. You cannot fix the value of R. And once electron may lie here, electron may lie here, anywhere in this fuzzy ball. And so the value of R is not fixed. And once the value of R is not fixed, let us suppose that this distance epsilon is epsilon, and it is, of course, it is lambda c, this epsilon, and then it means that in the variation in the value of r, the variation is plus minus epsilon somewhere it will lie, and uh, the potential, what we have assumed that it is exactly equal to z square by 4 pi epsilon 0 r. R is not fixed, so r is not fixed means needs correction. So what is the value of the correction with respect to the assumption that it is fixed? And so we shall discuss about it and then find it out what is the correction term into the potential energy. And that correction term is this one, S3 dash. So how we have come to this point, it is called Darwin term also. It is analyzed by Darwin, and so it has come to this point. So how we have got it? So I will take you to another slide somewhere, because it is, I could not make it this slide in continuity due to the shortage of time. So now I will take you to another slide in PowerPoint, and I shall discuss with you there. And so let me yeah, stop here sharing and then open another slide. Uh, okay, so another slide is the yeah, another slide.
So the next slide which you want to show should be
Yeah,
already
yeah.
open on your screen.
Okay, so I wanted to share it.
Yeah,
Yeah,
if it is already open, then you have to choose share screen and then a window from it.
yeah. So application window, I'm doing it, but it is not coming anyway. It has to come. Uh,
If it is already
and
open on your screen, then it will
yeah,
allow
now
you
it has
to
come. Now it has come. Now it has come. Okay, now it is shared. Yeah. So I'm not very expert in these things, so I'm
No
taking a
problem,
few
sir. Most
few
teachers are
seconds for
learning.
that.
Most
Yeah,
teachers are learning, sir.
yeah, yeah.
Sir, you can do
So
screen show.
now you are able to see the PowerPoint screen.
Yes, sir. But you have to
Okay.
click the presentation mode or slideshow mode,
Yeah,
which
yeah.
is
That time.
yeah, exactly. Yes. Perfect.
Okay.
Perfect,
That's
sir.
fine. Now I'm coming to my slide. So I will show you two slides here, and then I'll go back to my notes again. Okay. So this kind of thing I have done something messy, but anyway, it will take you a few minutes, a few seconds, and then I'll continue once again. So I was talking about the same figure here that related to Darwin term, that it is nicely written that even electron is considered to be wheresoever, either in potential energy or wheresoever, electron is considered to be a point charge. It is its instantaneous position of electron. It cannot be defined more precisely than within the volume. Actually, you cannot precisely locate the position of the electron. And so we cannot determine the position, but only we can determine the fuzzy ball of the size lambda c. That is the quantum wave. And so the potential what we are defining into the Hamiltonian, it is basically the effective potential. So the effective potential can be written in this form, that is V effective is equal to 1 by volume and integration. Volume is now, this potential is now function, not function of R, but it is a function of R plus epsilon. Epsilon is the this radius of the fuzzy ball. So this is a mathematical tool. Now what we have to do, V R plus epsilon, we have to expand mathematically. It can be expanded. I am not going to the detail which expansion, what expansion, but this can be expanded like this. And once it is expanded like this, then we have to see one by one that if you integrate this, if you integrate this, if you integrate this, will be up to this part. Rest is we shall not touch because it is not much significant. And so once we are integrating this we are getting the same volume, that is potential multiplied by volume. That is the same thing we are doing. But if we are integrating this part, it is a spherically symmetric part, so it will be equal to 0. So this is the mathematics. Next slide. So last part would be the correction part. The last part, once we shall integrate and find whatever it is. Because of that, we have already got it here, that assuming that R is the position vector, and it is very precise. But this is the part because of that, and next part also, but we are taking this the most significant part only. And then if we integrate it, so if we integrate this last term, it would give a result close to full relativistic correction term, and it will give you, I'm not going to details of the integration, it will give you x3 dash is equal to, that will be taken as a correction in Hamiltonian, 1 by 8 h cross by mc whole square del square. So this term will come. And so the V effective, what has been used into the Hamiltonian was VR plus this term. You see that we can further write it. Write this delta square V. It can be written as delta square V. What is that? Minus delta square. What is V? Z square by 4 pi epsilon 0, and then 4 pi delta R and something like that. So finally, you will get this S3 dash term in this form, in the form of derivative. Actually, there is a Laplacian derivative in which this delta square 1 by r is equal to 4 by delta r. I will define this, what is delta r. Then, so finally, if you introduce this delta r, you can write this. Sorry, you can write this this. Uh, uh, yeah, find this S3 dash term pi h cross square by. So there is a lot of background mathematics is involved here, and so I am being atomic physicist. I don't want to go to that part, but only thing that S3 dash is very important, and it is related to this delta function, delta r. And so I am going again back to the same thing. That is what where I had discontinued to do, and so I am closing it, and yeah. So let me first close it, and then I'm going to share.
Sir, please keep
Stop
your
share.
mic. Sir, please keep your mic next to your mouth, because if
Yeah.
it is,
Okay.
otherwise your
Okay.
voice is not clear.
Okay. So I'm going to again my that slide. What was there, and you see this is the mm, yeah, application window. Okay, and share. So I'm coming back to my previous slide, what I was showing you. And so this is the Darwin term. I explained, I actually for explaining the how it has come, I had gone to that my slide. Actually, I couldn't find time to write in continuity, and that's why. You see that property of delta function, most of you must be knowing that delta function, any value delta x is equal to 0 for x is not equal to 0, and delta x is equal to 1 when x is equal to 0. So this is the delta function, and this is the property of the delta function, that if you any function fx and you multiply it with the delta function dx, it will give you the value of that function exactly at the origin, at the x is equal to 0. And so uh, so we can write it minus infinity to plus infinity. We can show here again to you that delta E3, that once we know the S3 dash value, that is the correction term into Hamiltonian, then we can find by taking the expectation value, by taking this expectation value, and then delta E3 by this term, that exactly this term would be um, kept here, several terms will be taken out, and actually we shall write psi n00 r delta r. So this is the main task, how to find it, to find the delta E3 value, that is shift into the energy because of this potential. And so it is basically, you know that when R is equal to 0, then delta R will be equal to 1. And R, when R is not equal to 0, delta R will be 0. So this term would be valid only for when R is equal to 0 and it is equal to 1. So basically this term would be reduced to psi n 0 0 0 whole square. And so psi n00 whole square, we can find it out. And we have already done it earlier. What is the value of that? And so we put it over here and we find the pi h cross square twice. And this term can. And so in atomic unit, things becomes more simplified. And so E3, the several terms will be cancelled in numerator and denominator. And finally, you'll find minus En by Z alpha whole square by N. This term will come. Okay. Now we have to we have to um, we have to make it that we had started from this beginning, uh, uh, giving the idea that this the whole expression is working for L is equal to 0. So this expression, that is the energy shift, is only for the spherically symmetric s orbital and for L is equal to 0. So to confirm that, or to make sure of that, it will be multiplied by another delta function, which is written like this, delta L0, and its simple meaning is this, that when L is equal to 0, equal to 1, and when L is equal to the delta will be equal to 0 when L is not equal to 0. Means that this delta E3 will be valid only when L is equal to 0. Okay, as in the previous case of spin orbit interaction, that it is only valid for L is not equal to 0. So let me summarize once again that this is the expression for uh, this is the expression for the kinetic energy correction, mass correction. This is the expression for the mass spin orbit interaction, and this is the correction into energy or shift into energy because of this Darwin term. So these three correction terms had been found, H1 dash, H2 dash, H3 dash, and because of that, shift and splitting into the energy has been found this way. So it means that uh, if you are writing the Hamiltonian, you have to add these three correction terms into the non-relativistic Hamiltonian also. So H0 plus H1 dash, H2 dash, and H3 dash all will be there, and this will give you these corresponding energies. So what will be the total effect? Total effect onto the energy level, that what will be the total shift into the energy of En non-relativistic or Bohr energy when it will all three will be taken into account. So now all the corrections are relativistic in terms. So total relativistic corrections, which gives you a fine structure into the energy level. So now the task is this, that what is the total effect of three corrections? Okay, so now onwards, I shall discuss about what is the total correction. So you see, delta E, total delta E is delta E1 plus delta E2 plus delta E. So One by one we can see one condition. You know that all these delta E1, delta E2, delta E3, they have certain terms like you have seen here that we have three. We can, one thing I will tell you that again, if we convert all these expressions into a total angular momentum J, then you will find a very common formula for all these delta E and the summation of all these. And so let us start from this assumption that for J is equal to L plus half and L is not equal to. Once L is not equal to 0, it means that delta E3, that is Darwin term, will be equal to 0. And so only two terms will be added, and you add here delta E in this case only. Delta E is equal to, this is the correction due to kinetic energy, and this is the correction due to the spin arbitrary correction. Whence L is not equal to 0. And you see, once we have taken it that J is equal to L plus half, then only the L term has been cancelled. In the denominator, only these two factors of L exist here. Okay, so for J is equal to L plus half, and L is, it means that we are converting this expression into J only, and so J is equal to L plus half, L is equal to J minus half, and so if put it all these values here in terms of J only, then you will write this expression, that is En, that is 3 by 4 minus n by j and plus, and simply this is the manipulation and the rearrangement, and after rearranging you will find that delta E minus En z alpha by n whole square is equal to 3 by 4 minus n divided by j plus half. Okay, and so this is the expression. We should note it down that for j is equal to L plus half, this expression will come when L is not equal to 0. Yes, please come. Class. Class. Okay. So I'm sorry. Well, now for j to L minus half and L is not equal to 0, the same thing you do uh, here in this kinetic energy part will remain same. The part which is the spin orbit interaction, here it will be changed because you know that this part will be cancelled because we are taking j is equal to L minus half, and then we shall be simplifying this, and delta E for j is equal to L minus half, you will find this expression. So you compare these two, this and this is the same expression. So for j is equal to L plus half or for j is equal to L minus half, the same expression you are getting. And third one, for L is equal to 0. You know that for L is equal to 0, only Darwin term will be taken into account. And you see that then in that case, the spin action contribution will be 0. And so at a time, only two terms will be added, delta E1 with delta E2 or delta E1 with delta E3. Delta E1 will always be common. So you see that here, if we are taking L is equal to 0, means delta L, the delta L0 will be equal to 1. And so we add again. This is the kinetic energy part, and this is because of the Darwin part. And you see, we are putting it again, this expression, and you see that is equal to minus En by Zn square, and putting the value of L is equal to 0, and we are uh, simplifying it, this equation for L is equal to 0 as this. But one thing is very important here, that for J L plus half, here L to 0, J is equal to half. Here L minus half, L is equal to 0, so J is equal to minus half. Why it is forbidden? Because we are talking about the magnitude here, and so only 1/2 will be taken into account. So J is equal to half. So J is equal to half. If we are writing here, you know that here n can be written as, it is just it is, these kind of things are not written in the book. N can be written as n by 1, or it can also be written as n by half plus half. And what is half here? First half is j, and so we can write in this form j is j plus half. The same expression can be written for L is equal to 0 also. L is equal to 0, j will become half, and so it is equal to. So you can see this expression, and this expression. So it means that if you are taking this E and J, why I am writing E and J here now? Because you have seen now that a common expression for the delta E, that is total energy shift, common expression is depending upon the principal quantum number and the J value. These two, the values and quantum numbers are important. And so the energy, they either shift in energy or the total energy, it depends on the value of n and j. The shift into energy is depending upon the n and j, and the non-relativistic energy, it is only depending upon n, that is principal quantum. And so if you write in a combined fashion, you can write like this. And so En is equal to minus z square by n square. So you can write this delta E and j in the form of the Rydberg also. And so this is called total correction. Generally, we write it either into the atomic unit or in the form of Rydberg. Okay. So now what to do on the basis of this discussion? I have framed few numerical problems, and through these numerical problems, few things will be clarified to you, so that during your revision or during your certain examinations, you solve the problem a little bit easily, instead of going stuck into several things which is really not necessary to go through. And many things are out of our thorough analysis during the class continuously, and many things come out of our experience. And so this I would like to share with you while solving the problem. Okay, so you see, you know that in the total energy, there is always one condition, that's in a single electron system, the total energy or the shift in energy, it depends, as I told you, depends upon the value of principal quantum number and the value of J. J has two possible values if there is a single electron. So single electron case, the two possible values is L plus half and L minus half. It means that if you have, suppose if you have any non-relativistic energy, which is also called Bohr energy, and shift you are talking about, and shift overall, all these analysis was mm, done by in the era of Dirac, and so these shiftings are known as the Dirac energy, the Dirac energy shift. Okay, so the Bohr model and this is the Dirac model, and according to that, in the Bohr model, if non-relativistic energy is En, then because of these mass corrections and various types of corrections, total energy corrections you are calculating, then there will be shift into energy. But shift into energy is depending upon J, and J has two possible values for one electron system also. And so J will be L plus half, you can say it as J dash, and J double dash, it will be L minus half, that is J double dash, you can say it. And the shift from the En will be, I can show you the diagram, that there will always be shift in, then there will be two lines always corresponding to J L plus half corresponding to J double dash L minus half. And so if it happens, it means that in the shifted lines of the energy, there will always be a gap. And this gap between two energy levels, this energy difference, is known as fine structure splitting. This fine structure splitting is a very important parameter. You see that for the p electrons, for d electrons, for several electrons, these two lines will always be there, and that corresponds to J is equal to L plus half and J is equal to minus half. Okay, minus half. Okay, and so the question is this: what is the energy difference between the two lines corresponding to J dash and J double dash? So this separation can be written as delta E J dash J double dash. Numerically, you can find it out. The shift corresponding to J dash and shift corresponding to J double dash. Then you can write the expression. You have the same expression here, and corresponding to J value only be changing. And so then you can write a few things may be taken out, and this is N L plus half and then minus 3 by 4 and L minus half. So here, when L plus half, then it will be L plus 1, and that is half plus half, and when L minus half, then it will be only L. So from here, you can find and just manipulate and just rearrangement, you'll find an expression that is Z is for 4 alpha square by n cube L L plus 1. So this is the separation between the two lines once it is corresponding to two possible values of J. And so just for the sake of simplicity, we have noted it, we have taken it, this Z power 4 alpha square for any given the, the state or atomic number, this C Z as a constant, and then this is equal to, so it is not a, it is depending upon the element what you are taking, and it is a state. So Cz by n cube L. So it is, this difference is called the fine structure splitting. Okay. So this you keep it in mind, and sometimes related with this, some numerical questions used to appear in the question papers. Okay. Now another question. Another question is find the fine structure energy shift or total energy shift. I want to clarify. If sometimes in the question paper, if you are getting this terminology, find the fine structure energy shift. So don't think that it is not clarified which kind of energy shift we are asking. Fine structure, kinetic energy, or spin orbit, or potential energy. Actually, if this kind of terminology is written, it means that it is total fine structure energy shift we are talking about. So for the total one, the same formula will be taken into account from here, that the same formula will be used in such kind of expressions. Okay, so find the fine structure energy or total energy shift due to relativistic correction of the state of hydrogen and helium. You know that hydrogen is one hydrogenic system, and helium plus, that is one electron is trapped another hydrogenic system. Difference is of value of Z. One has a Z value equal to 1, other has a Z value equal to 2. So the solution is given here, and that is 1s state. For that, I was 1s state of hydrogen, then n is equal to 1, then L will be equal to 0, and J will be equal to half. For J is equal to L plus half, you write this expression in the Rydberg, and delta E is equal to J equal to half. That you can write Z to the power 4 from here. That whenever you put all these values, you'll find L is equal to 0. So it will be J is equal to half Z square by alpha square by 4 Rydberg. Now, what is alpha square? Here I want to clarify you, because the main purpose of uh, doing this numerical problems, it is not simply a addition multiplication. It is simply putting the values. Some things what you need to be clarified while doing the numerical problem. What is the alpha square Rydberg? Because Z square has no any dimension. So if delta E is coming into Rydberg, means alpha square is expressed in Rydberg. So alpha square Rydberg, it will be written how? How will you write it? If this is written, it will be a Rydberg constant, experimental value, and divided by 1. The alpha square means that uh, 1 by c square. So once Rydberg is divided by 1 by 37 square in atomic unit, then it will give you 5.84 centimeter inverse. So students are advised that wheresoever in the numerical problem, if alpha square need to be written, if it is already given in Rydberg, then if it is need to be converted to centimeter inverse, simply you write it alpha square in centimeter inverse, its value will be 5.84 centimeter. You see, and so written here, that is delta E J is equal to half equal to this, where C is what? C we had, this is the alpha square we had written for um, yeah. So it is simply you can write it that Z square by 4 C.
Professor Hashmi,
Yeah.
sir, there is one question in between. The
Mm.
student asked that I am confused a bit. Hydrogen atom non-relativistic. Why do we need to calculate relativistic correction in terms of energy? I thought that before you proceed further, maybe this should be clarified.
The question again, please.
Yes, sir. So, sir, the student writes that I am a bit confused. Hydrogen atom is non-relativistic. Why do we need to calculate relativistic correction in terms of energy for hydrogen atom?
No. What hydrogen energy is non-relativistic.
No, he is right. I don't know whether you meant this or he has understood like this. Dinesh Singh
No,
Mehra
he
says that
understood like this.
hydrogen atom is not non-relativistic. Why are we
No, it is
calculating
not.
relativistic correction?
No. The entire story, what I am telling you, all the students, it is related with the non-relativistic, the relativistic approach of non-relativistic particle. Hydrogen is not non-relativistic particle. Hydrogen are hydrogenic system having one electron system. Once we have treated it with the non-relativistic approach, the energy is En. But if even in the single electron system, like hydrogen, if we all those corrections, relativistic corrections, it is a non-zero value you get in terms of energy, in terms of shift. So relativistic correction is always there, even for hydrogen. He should not uh, be adamant and the fixed opinion that hydrogen is a non-relativistic particle. Once you are calculating energy from the non-relativistic approach, it will be there, the En value will be non-relativistic. But for the single electron system, which is hydrogen is also single electron system, there are certain corrections And these corrections are because of the three correction terms we have discussed. And this is the total energy correction we are getting. How can you say that there is no need of doing correction in energy for the hydrogen atom? It's not like that. We are studying all these things only for hydrogen and hydrogen-like systems. Okay, so uh, yeah, so I should proceed.
Yes, sir. There is this one small query that why about the mass of the electron. Why is it taken
Hmm.
to be equal to h cross 1 by 4 pi? I did not understand the question very well, but
I'm
regarding
not
mass of
able
the
to get it.
electron,
Mass of the
see it in
electron.
them. Maybe you can see it in the end. When you finish
Okay, okay.
sharing, then you can look at the
Yeah, yeah.
question.
Okay, I'll do that. I'll do that. But definitely, mass of the electron is not h cross by 4 pi whatever she is saying. Yeah, yeah. In atomic unit, it is taken to be equal to 1. Okay, so delta E j is equal to half. We are getting a particular value. So for hydrogen, this is a term. So for hydrogen, it is Z is equal to 1. So delta E j is equal to half. You can find this much shift. You can see that from the Bohr's energy, there is a shift, and this is called, this shift is the Dirac shift, and this is because of these three corrections. So there is always a shift, and you can see that how it is depending upon the value of Z. Z is a very important factor in this case because the shift depends on the value of Z enormously because it is with the power of the 4. So if we are taking helium, then this shift is quite large. You can see that this is the 1s state of hydrogen atom. You see when n is equal to 1, its energy is minus 13.6 electron volt. In 1s state means in ground state, and this is the according to Bohr model. And according to non-relativistic Schrodinger equation solution, En is coming like this energy. But if you include the mass corrections, total mass corrections, so total mass corrections are depending upon the value of J also, not only N, and there is a shift into this the energy En, and this is the shift. And this shift will always be according to the value of J. J will be L plus half or L minus half, and you see that you are getting this much energy. Uh, and for 1s state, it doesn't lie. But for hydrogen atom, this shift is minus 1.46, and once value of Z is just double, then it is very high, minus 23.6, comparatively very high. One thing is very okay. One more thing I would like to mention here for students, that generally the energy is expressed. We start from the joule, but for the atomic energy and for the atomic scale, we mostly represent it in terms of electron volt. And you already know that how to convert the joule into electron volt. It's very easy for you. But anyway, now that these energies are always, I'm writing in terms of centimeter inverse. What do you mean by that? Uh, I'm also telling you, the MSc student and even BSc student, if you see some spectra like infrared spectra and Raman spectra and various types of spectra, in the x-axis, where you know that in the y-axis it is intensity of the spectra, and in the x-axis we always write in terms of energy variation. So energy variation or frequency variation, it is the same thing because energy is equal to h nu. H is the constant. So either variation is in terms of nu, or if it is in terms of the frequency, it is also the energy. It is the same thing in the spectra wheel. But generally, it is always written in the x-axis centimeter inverse. Uh, so I would like to clarify that this is basically wave number. So the wave number is always represented by 1 by lambda. You know, then always all the spectra are represented by centimeter inverse. And so it is for simplicity that actual variation it is in lambda. Actual variation is not in the constants. The constant involved in the energy, you see, in terms of lambda, if you write, then what is the expression of energy? It is equal to hc by lambda. So hc, if you are taking it as a constant and you put it out into the left hand, in the right hand side, it will be 1 by lambda, which is actually varying. So for making it more simplifying, then 1 by lambda, in terms of that, we all the spectra are recorded in terms of 1 by lambda. 1 by lambda is actually wave number, which is represented by nu bar. Okay, so nu bar equal to 1 by lambda, and it is equal to E by energy by hc. So if you want to convert the electron volt energy into centimeter inverse, just convert. There will be a conversion factor, and that conversion factor is 8065. So what is this 8065? Means that 1 by lambda, which is in centimeter inverse, if it is conversion factor you want to find, then hc you calculate for 1 electron volt, and then 1 electron volt divided by h. H value you also write in terms of electron volt into second. Generally it is 6.63 into 10 to the power minus 34 joule second, but you write here in terms of electron volt, which is equal to 4.153 into 10 to the power minus 15, and value of c you write into centimeter, that is 8 into 10 to the power 10 centimeter per second, and then you will find the value 8065. So 1 electron volt is equivalent to, so you know that if you have any spectra in which intensity as a function of this wave number centimeter inverse is expressed, in order to convert it into energy, this conversion factor you remember 8065. So once you will divide it with 8065, it will become converted into the electron volt. Okay, and so here, if it is written something 1.46 centimeter inverse, this shift in energy, if you want to convert it, suppose some teacher has asked you that you express it in terms of electron volt, keep remember that you have to divide it by 8065 and find the value either here or here. Okay, and then this is the another question what I have written for you. Find the energy shift for 2s and 2p level. Here what we have demonstrated that how the effect of z the influence, how the value of z affect or influence the energy shift, and you can see that since this value is in energy shift is proportional to z to the power 4, it gives a very large difference from one element to the another element. in the hydrogenic system. Secondly, here we are uh, we are giving a demonstration that suppose we have a hydrogen atom and we are calculating the energy shift, total energy shift, and the electron once it is in the s orbital and then electron is in the p orbital, then what will be the difference? Same thing can be demonstrated from here, that if s orbital value will be different, p orbital j value will be different with respect to each other. And then you can see that for h, z is equal to n, 2s electron, then these are the parameter, n is equal to 2, n is equal to 0, j is equal to half. Put all these values over here and you will find that it is equal to 0.456 centimeter. So just by simple calculation, you can find it out. Then you come to this 2p electron. Here, the same electron in the same level, but 2p electron. So electron position is from one orbital to the other orbital. You see L value is changed, and then the two possible values will come out because uh, J here L is not 0, and so it will be either 3 by 2 or half. And so, depending upon the J value, either half or 2, now there will be splitting into the energy. So, the electron, once it is in the S state, it will give a one energy shift. But if the electron is in P state, it will give two energy shift because of the value of J, and there will be splitting into the line. So you literally see it into the spectrometer, these splittings because of the shifting and because of these mass correction. So all are these are the beyond the Bohr model, beyond the Bohr model, that we are taking into account all these kinds of correction terms and relativistic corrections, and because of that we are getting all these possible shifts. And you can see that for j is equal to half, the value you calculate, and it is minus 0.45. Similar system means z is same and n is same, but j is different. So minus 4.6, and it is delta E when j is equal to 3 by 2, then it is equal to minus 0. So you can see here that when the electron in the same orbit, and if it is in s orbital, then there will be a shift from here to here, and from the energy, it is the Bohr non-relativistic approach, and it is the Dirac relativistic approach, and then there will be a shift into that, and that shift we have calculated. But the same electron, suppose we are treating it into 2p state, same state, but in the p orbital, two possible state will lie. So it is at 2p 3p2 and 2p half. So you know that electron is bound in the suppose single electron is there, and it is bound into the atom, and it is whirling around the nucleus. According to the value of J and value of N, their binding energy means the energy required to knock off those electrons from there would be depending upon various parameters. You see that when Z, if it is increasing from 1, 2, 3, 4, from hydrogen to lithium to boron to beryllium, then binding energy will increase, because it is related to Z to the power 4, and so more energy is required. At the same time, when n is increasing, that is from one orbital to the other orbital to the other orbital, binding energy will decrease because it is in the denominator you had seen. And so from one orbit to the other orbit, if electron is there, then if it orbit is it is going from one state to the higher orbit, it will be binding energy will decrease. And so it is depending upon J also, that when J is increasing, then binding energy will increase. will decrease. You can see from the expression. So, so two examples you have seen, and then, ma'am, we have some 10-15 minutes time. Hello?
Yes, sir. Yes, sir.
Yes, sir.
Sir, we have 10-15 minutes.
10-15 minutes. So I will switch over to another slide, and then.
Sir,
Uh,
excuse me, sir.
mm,
Sir, there are some questions students have asked. So, would you like to answer them at the last, or will you take up now?
uh, what is the procedure? What do you think that
No,
I should do?
it's totally up to you whether you want to take
Uh-huh.
it at the end or you want to take it now. It's totally up to you.
Okay. Actually, I'm feeling not very convenient through this mode of communication. That
Okay,
how
sir.
should to answer? Is it not okay if the student uh, can mail me and I give the answer? Is it okay?
Yeah, sure, sir. Sure, sir.
Yeah.
We will give me email ID to all these participants. They can ask the
Uh-huh.
question there.
Yeah.
No
And then
problem, sir.
I will definitely give them a satisfactory answer from various things. So
No
I want to
problems.
cover one numerical more numerical problem.
Sure, sir.
Uh,
Sure.
yeah. Okay. So
Sure, sir.
so I want to shift it to the another file. Are you able to see that this one? No.
Uh, Sir, we are
Let
able
me.
to see find the energy correction due to spin orbit interaction
You
property
are able to
JP.
see. Yeah.
Yes, sir. We
You are
are
able
able
to
to
see
see.
this one. Na?
Yes, sir. Yes.
Okay, that's why.
Yes, sir.
Otherwise, I thought that I should go stop sharing and go again. So
No, sir.
it is
It's
good.
visible.
Okay, it's visible. Okay, that's fine. No, it's okay that in the same PDF file I can switch from one file to another file.
Yes, sir.
Yeah,
Yes, sir.
yeah, good. So this is the another question. You see, in which I want to clarify you that, and I think that this is last question I'm going to discuss with you. That spin orbit interaction is such an correction term in which always it gives a two line that from the Bohr line of energy, non-relativistic line, once only if you consider the spin orbit interaction, you just don't think about the other types of correction, then it always lead to splitting, and you will see that that's why you know that it is only for L not equal to 0. So spin orbit interaction for 2p, 3p and 3d states of lithium, I am taking the example, and find the energy correction due to this spin orbit interaction. And you see that this is the common formula for uh, mm, uh, for the spin orbit interaction, delta E2 alpha square z to the power 4 twice n cube L plus half and L minus L plus half L plus 1 for j is equal to L plus half. Okay, so this you can see from your previous slide that this is the formula for j is equal to L plus half. And so for 2p electron, there will be uh, there would be uh, two states according to the value of j, 3 by 2 and half, and so one by one we can find it out the delta E2 values, that is corresponding to j is equal to 3 by 2. You will find uh, here 9.855. You just put the values here, 5.84 into 3 into 10 to the power 4. Why 3 here? Because I am taking lithium. Lithium has 3 atomic number, and then already there n is equal to 2 because n is already given to you, n is equal to 2, and then L is equal to 1 for corresponding to the p subshell, and so L is plus half and L plus 1. 1 plus 1 and half. And then from this, you can find it out the 9.855. So this is the shift corresponding to J is equal to L plus half. But corresponding to 2P minus half, the formula will be different with minus sign. Why with minus sign? Because you may have seen there is a factor here that one L and another one is minus L plus 1 when J is equal to L plus half. So the formula is changed and you put all those values and you will find minus 19.71 centimeters. So for 2p subshell, one electron is there. If it is lying in that, then corresponding energies will have splitting of the two energy corresponding to delta E2 with J is equal to L plus half and with J is equal to L minus half. The same thing you can find it out for 3, means that for the higher orbit and for the then in higher orbit you can see these values are reduced from 9.855, now it is reduced to 2.92. So this shift reduces for the same p orbital, but for higher orbit, then value as you go up, then this shift will be lower and lower and lower. You can same way you can calculate. And then for the 3D electrons, for that means that if you are now changing from p subshell to the same electron, if you are going to subshell, then L will be equal to 2 and then J value will be changed, and then it is a lowering into the shift into energy plus 1.165 and minus 1.7. So accordingly, if you are drawing the diagram, so this is the 2p state. This line is representing when it is a Bohr model is taken into account. But if all these shifting is we are doing it, then all these shifting that in the spin orbit interaction will always be a shift towards positive side and shift towards negative side. There will always be a shift, and always you have one electron system, so always it will have two states corresponding to J plus half and J minus. You see, and one is plus, other is minus. One is plus. Now the amount of shifting will be reduced because now N is going up from lower 2 to 3. Then it is shift is lowering. But when the same level, if from P to 3D states, if we are shifting it, then again further lowering into the splitting you will find. So this kind of splitting and their amount of shift or amount of the shifting, it will be depending on the three important aspects. One is the value of Z, another is the principal quantum number in which orbit electron is orbiting and in which orbital electron is lying. So from the degeneracy, you have already learned that on the same energy level, En, there are other possible states in which electron can lie, and so other energy states also exist in which electron will lie, and so these are the energy states. And because of the shifting and non-relative phenomena, you are able to calculate, and it is very close to the experimental value. So these are called the fine structure. So these were the fine structure. There is another approach that is also what we are not going to, maybe some other teacher may discuss with you. That is called hyperfine structure. Hyperfine structure is also there, but it is another topic, extension of this topic. So this is the fine structure. So it is a simply another question I have not touched, but it is very simple. You can do from the splitting, fine structure splitting, but it is not very complicated question. You can do that. Well, so I have tried my level best to uh, make you clear that if you have a hydrogen atom or hydrogen-like atom, one electron system. So if you have a concept that it is a non-relativistic particle, electron which is whirling around the the nucleus, it is not non-relativistic. It is relativistic because Bohr's model, based on their postulates, they have given one energy, but that energy shift is always there if you introduce the relativistic corrections. And these corrections are three, and all are combined. You can do that. You can see the shift. So I think that if you have this concept that electrons into the hydrogen atom is not relativistic, it is not correct. Okay. So I think that I'm closing to the time which is given to me. And one thing more, that I have given the message to your teacher, that if you have certain questions and queries, I showed you my email, or you can take from the co-host, and you just send me the query. I will definitely give you. And if you have a group of the students and you are having some idea of sharing with each other, I will definitely reply it. But during the short period of time, it is difficult sometimes to give you satisfactory answer. Uh, uh, I hope that you will write to me. Yeah. Thank you very much.
Thank you so much, sir. It's very nice, and we still have another lecture with you, and I think this will further clarify many things. It's true that covering atomic physics in a small time of 1 week is difficult.
Yeah.
However, it gives a very good idea of where to focus upon, what to keep in mind, and not every
Yeah.
line is to be prepared, and that
Yeah.
we
Yeah.
should think of on
Yeah.
priority basis what are the things that you must take into account.
Main
If
thing
you
is
are
this, that
really
many queries the students have in their mind, and if
yes, sir.
their queries are cleared, then it will be very helpful in preparing the further the things into
Yes, sir.
atomic physics, or even any subject. It is very
Yes, sir.
useful.
Yes, sir.
Yeah.
So,
Yeah.
sir,
Yeah.
tomorrow after your class, I would be collecting their questions, and
Okay.
if required, then I will be passing them on to you for clarification.
Yeah.
And
Thank you
the
very much.
PPT and the papers that you have shown for delivering your lecture, you will
Yeah.
kindly pass them on to me, and I shall pass them on to the students.
Okay. No problem. No problem.
Thank you
Yeah.
so much, sir.
Okay.
Sir, it
Okay.
is
Thank
indeed
you
a
very much.
great pleasure to have you here with us. Thank you once again.
Okay.
Thank you,
Okay.
sir.
So I'm stopping sharing. Yeah.
Yes, sir. Yes, sir.
Yeah. Okay.
So, yes. And now, Dr.